Hello and welcome to this presentation where I'll be showing you how to use computer simulation to improve the management of a golf course and maximize its revenues. But first, a little look at the computer model. This is a very simple representation of a golf course where we have 18 holes, numbers H1 through H18, represented by machine with this software. And in front of each hole there's a queue or a waiting line, waiting area, if you will. So as we will see later on, I'll be running from the start of the day with foursomes coming into the first hole, and then filling up the whole golf course. So let's put that aside for a while and take a look at the presentation. So golf courses have to manage two objectives. First one, to manage the number of players on the golf course in order to maximize course revenues. Second one, to minimize the wait time of players on the golf course in order to minimize player frustrations. Main variable to control here is the tee time interval, but there's also marshal enforcement as well as skipping and passing policies. Also, shotgun starts behave differently. So the objective of the simulation is to better understand the impacts of the tee time interval on the two objectives. First, maximize number of players during the day and minimize player wait time or total play time. A second objective is to better understand the running of a shotgun tournament and the impact on wait time of the number of holes occupied in that shotgun. So first we'll do a very basic model with 18 identical par 4 holes, which is normal 72. Each hole with a random play time according to a triangular distribution. So triangular distribution is of average play time is 13 minutes, minimum is 10, maximum is 18. Represented here as the probability distribution looks like this, which means you have a greater probability of being around the average and less of being towards the extremes. These parameters are estimated. They haven't been measured. They're based on experience. Of course, these could be measured to improve the accuracy, but might not change the conclusions of that of what we'll be doing today. So the random playtime is regenerated at every hole for every foursome, meaning that no foursome is consistently fast or slow. They're all equal or equally good and bad. So they all each have the same chance of being good or bad at every hole. All holes can accommodate two foursomes at the same time, and in the simulation model, a foursome is represented by a person. And the tee time interval to start with will be every 8 minutes for 8 hours. So what the result looks like, so we have 60 foursomes that finish during the day. Average play time 4 hours 15 minutes. Maximum play times 4 hours 32 minutes, and the minimum play times 3 hours 56 minutes. And only one of the 60 foursomes takes more than 4 hours and 30 minutes. That's probably the 4 hours and 32 actually. So, and this is what it looks like. As you can see, during the day the play time slightly increases, but it always stays at a reasonable delay. Next, we tried to be a little bit greedy and reduce the tee time interval to 7 minutes instead of 8. The results is that we can put in 15% more revenues, 50% more foursomes during the day, 69 instead of 60. But the play time is really unacceptable. On average, 4 hours 36 minutes, up to almost 5 hours in some cases, and 3/4 of the foursomes take more than 4.5 hours to play. So that's rejected. As you can see, the play time becomes really long after a couple of hours have elapsed. So that's unacceptable. Next scenario is we'll do the opposite. We'll increase the tee time interval to 9 minutes to see if we can reduce the play time. So we have 10% less foursomes that are able to play during the day, 54 instead of 60. Average play time is just 2% shorter. It's barely a difference. It's 4 hours 11. almost 4.5 hours for the maximum, and 3 hours 52 minutes for the minimum. So we don't have any significant improvement in playtime, but we have 10% less revenue. So that's, again, unacceptable, rejected. So the conclusion of that first simulation is that if we have 18 identical par 4 holes and we test it with tee times of 7, 8, and 9 minutes, the conclusion would be that 7 minutes is unacceptable, 8 minutes is a reasonable 4 hours and 15 minutes, which is normally accepted playtime. 9 minutes doesn't increase the playtime but reduces the number of foursomes by 10%. So this would indicate that 8 minutes is the best tee time interval to maximize the number of players and minimize the playtime. We haven't tested fractional tee times like 8.5 minutes because realistically it's really difficult to apply in real life. Simulation 2, we will test a more standard golf course with the following parameters. So we'll have 4 par 3s, 10 par 4s, 4 par 5s. We'll have they'll be at these hole numbers, which is actually based on a real golf course around here in Montreal where I play. These are the triangular random playtime distribution, again estimated for each par type, and how many foursomes can be on the hole at the same time. As you can see on the par 4 it's 2. That's what I had used in the basic model. That's standard procedure on a par 4. You have people that are on the green, the other one near the green, and the other ones can start. On the par 3 you only have 1 foursome at a time, and on the par 5 you could have up to 3. One in the fairway, one at the start, and one on the green. So we'll use the tee time interval that we had evaluated as being the optimal before, and see what it looks like with a real golf course like this. So performance measures that we obtained, the results we obtained, well, we have again 60 foursomes during the day. We have 4 hours 12 minutes average playtime, 4.5 hours maximum. This is very similar to what we just did before with 18 identical par 4s. So it means that it doesn't really make a difference on the total, but it makes a difference at each hole. So if we look at it on the right hand side here, we have for all the holes what type of par it is, what's the minimum, maximum, and average wait time that people have waited, that foursomes have waited. And if I take that and I condense that and group them into types of par 3s, 4s, and 5s, we can see again very realistic wait time distributions that on average on a par 3 we wait 3.4 minutes, on a par 4 we wait slightly less than a minute, and we don't really wait on a par 5. Again, these are the averages, but you can have some extreme maximums which also occur in real situations. So third simulation, we want to see what happens when we have a shotgun start on that same course with the same statistically distributed time. So I'm not changing anything, but I'm doing it as a shotgun start instead of a regular tee time start. So we have 2 foursomes per hole for a total of 36 foursomes. Results: average playtime 4 hours 38, almost 5 hours maximum, and 4:13 for the minimum. And 81% of foursomes take more than 4 hours and 30 minutes to play. That's kind of a lot more. Like, it's about 10% more, 10% longer. But why? This is the same course, the same playtime distributions, but the total playtime is 10% longer than with regular tee times. Question is why? When we think about it, the average playtime is longer because we're filling the course right from the start with 2 foursomes at every hole. So right away, right then, after foursomes, start the game by waiting. You're forcing a wait from the start. And it's never going to improve because the course is full and everybody starts at the same time. So the situation never improves during the game. You never have the opportunity to catch up any lost time, and little delays accumulate. You can never say, okay, let's walk faster here to compensate. No, it's the way it's done is there's somebody in front of you always. So you never have the opportunity to catch up. simulation 4, what if we want to test the impact of not having a full course with a shotgun start? We don't always have 36 foursomes to do. So what we'll do is do a test. We'll run the model with 18 holes with 2 foursomes each, and then 17 holes with 2 foursomes each, 16, etc., all the way down to 10 holes with 2 foursomes each. We don't need to go to less than 10 holes, because if we have less than 10 holes, we would need 2 foursomes per hole. So that's not part of this scenario. So what I've designed is an experiment where I run 25 replications of each of those scenarios, and I calculate the mean based on 90% confidence. What we get is that the average playtime remains at or less than 4 hours and 20 minutes for all scenarios up to 15 holes occupied. So if we look at the graphic here, we're all 260 minutes is 4 hours 20 minutes. We're at or below that, or close, up to 15 holes. And then when we get to 16, 17, 18 holes occupied, then we have a steep ramp up of the total playtime. So this would indicate that the ideal number of foursomes on a shotgun in order to maintain reasonable playtime is 30 foursomes. So 2 per hole on 15 holes. Of course, that's just one scenario. There's many more simulations that we could be performing here. There's many more shotgun configurations with less than 36 foursomes than the ones I've simulated here. For example, we could have 9 holes with 2 foursomes and 9 holes with 1 foursome, and they could be alternating, and we could see what this looks like. And imagine any other combinations of foursomes. And also, the simulation could be tailored to each individual course layout and to its management rules. We could apply skipping rules, passing rules. You could all test those within the simulation. Parameters such as handicap levels could be considered in the simulation on an individual level, foursome level, tournament level. We could say, okay, what if there's one guy in each foursome that's really bad? What if these 4 foursomes are bad and these 12 others are good? I could test all these things. So even if we didn't think as a golf course as being a complex thing that required complex mathematical analysis, as you can see here, simulation is useful and can help solve important business problems and improve profits for businesses like a golf course. So for any questions, comments, or anything, don't hesitate to contact me. My name is Patrick Cloutier. You have my coordinates here. Take a look at my website, and I'll be glad to help you or answer any questions. Thank you.